So thanks a lot for offering me this opportunity. It is truly an honor. Also, it felt a little bit like a trap when I start preparing my lectures, because obviously this statistical mechanics is a very old topic. Oh, you can't hear me, maybe? Is that, what's the, okay, good, okay, perfect. Yeah, so it's a very old topic, and it's been covered obviously many times by people that are way more knowledgeable and wiser than me. So before I tell you what I can discuss, is it okay? You can hear me. Okay, thank you. Yeah, don't hesitate to interrupt me. I will put the chat somewhere. So if you want to just ask a question in the chat, I will try to check it. Yeah, so maybe let me tell you where you can find more detailed, more precise, better informed information about statistical mechanics. And these are references that I've consulted to prepare whatever I can tell you myself. So first of all, there's a series of lectures by Ivan Velenik. He gave them a few years ago at Swiss Map. If you Google Swiss Map, you will see the recording of his lectures, and that's 7 times 3 hours, so it's much more detailed than what I can say. And there are also lecture notes by Stephen Adams on his webpage. I think it's called Lectures on Mathematical Statistical Mechanics. That's from 06, and so you can find the PDF online. And there are several very good books. There's actually a book by Velenik and Friedli that I think is so it's really meant as a textbook. It's called Stat Mech of Lattice Systems, and then there's a subtitle, and you can find it online also, and that's from also, I think, 17. And I will quote sometimes chapters or excerpts of this book. There's a book that I've used a lot when I was doing my PhD by Sepalainen and Rasulaga. I guess it should be Rasulaga and Sepalainen. And that's called A Course on Large Deviations, on Large Dev, and Intro to Gibbs Measures. And that's also meant as a textbook. And so these are mathematicians. And there's a book written by a physicist that's who's very much a physical, a mathematical physicist, and it's a very interesting one. It's a more difficult to read, I think. So it's a book by Galavotti, sorry, and it's called Statistical Mechanics, a Short Treatise. And it's very interesting because it's very dense. It's sometimes hard to read if you're not a physicist, which is my case. But it gives you the physicist point of view on the mathematical physics treatment of statistical mechanics, and it has great insights. Okay, and then there are 2 references that you can consult, but I wouldn't suggest to go for them as textbooks. One is the classic book by David Ruel. So that's an older reference. And then there's a book by Hans Otto Georgi, which is also great, but not super friendly if you don't know much about it. And it's called Gibbs Measures and Phase Transitions. Okay. So if you read all of this, I think you're an expert in statistical mechanics. So I was wondering what I could say, and I thought that maybe what could be helpful, because obviously this is, there has been lots of treatments by people that are much more knowledgeable. I could give I thought I could talk to my inner self from 10 years ago and try to tell me what I wish I knew when I started my PhD, and maybe so some of the terminology, some of the intuitions that are not completely obvious when you start. Also, where to look things up if you don't understand something in that context. I mean. Yeah, so it's going to be a little bit informal, also because of time constraints. You can find all the proofs and all the very advanced discussions in those references. I will point to them when I can, and I will try to address the audience as a friend or as a younger version of myself, and explain some of the basic things that I've learned. During my PhD and so on. Okay, so I will start with some foundations and some basic concepts. So maybe the origins of statistical mechanics, right? So obviously, I'm sorry if you've already taken some class on statistical mechanics, or if you have a PhD in statistical physics or whatever, things like that, you may be utterly bored. I'm sorry, but don't hesitate to comment or to share your own experience or to share your own wisdom, because that can be actually pretty interesting. So if I want to, I can quote two of the references that I mentioned. If you look at the book of Friedel and Bilyk, you will see they define statistical mechanics as a theory that aims at bridging the gap between microscopic and macroscopic descriptions of large systems of particles in interaction. Large systems of particles in interaction. Okay, and if you read Galavotti, you will see that for him the goal is deducing macroscopic properties of matter from what he calls the atomic hypothesis. So really from the microscopic description of matter. Okay, so really the goal is to go from micro to macro. Sometimes it's hard to tell the difference with my accent. So in the microscopic description, you see matter as atoms or molecules, as elementary constituents. You know that these elementary pieces, they interact. There are forces between them or on them. Okay, and so if you want, the setting is to simplify is Newton's law of motion, right? So you can write equations for the dynamics of such systems. So it's classical mechanics of these tiny pieces. And so that traces back to, I guess, 18th century, right? And then the macro description, it uses words as heat, pressure, volume, what is a liquid, what is a gas, stuff like that. And the name of this science is Thermodynamics. And thermodynamics, what's interesting is that it's a phenomenological theory based on empirical principles. And that's more a 19th century business. Obviously, people have used heat and pressure before that, but the physical treatment was done in the 19th century. And the question is, can you go from the small scale description of matter to the large scale or human scale description of matter in some kind of physically or mathematically rigorous way? So maybe just to be a bit more formal, let me remind you of some of the classical framework for classical mechanics. So in classical mechanics, the way you describe matter, or one way that you can describe matter in that framework is you would say, okay, I have n particles in RD, and if you're a reasonable person, D equals 3, but typically in mathematics, we are not super reasonable, so we'll take D equals 1, 2, 4, goes to infinity. Okay, so but in the physical space, obviously, it's D equals 3. And they are, let's assume they are identical, and they are classical particles in the sense that we neglect relativistic effects, and also we neglect quantum effects. And we take them as being point particles. Okay, so they occupy volume 0 portion of space. I mean, each one, okay? And the way you encode them is you can just write down their positions, and P, so that's the position. And that's the momentum. So it's the mass times the velocity. And that's a vector in RD. The momentum is also a vector in RD times n, okay? And X will be the state of the system. And I equals 1 to n, okay? So you have 2 times d times n parameters here needed in order to describe the full system. Okay, and then laws of physics, they give you, well, depending on which particles we are looking at, if they have a charge, if they have a spin, if they have a mass, then there will be forces between the particles. And typically the way so it could be, you know, electrostatic or gravitation, whatever you can think of, as long as you can encode those forces into some Hamiltonian function. And it's going to be a function of all the xi's and all the pi's. So it's a function of big X. And typically the way it looks is something like that. You have some interactions between the particles, and then some interactions, or maybe some forces that are just acting on each particle, and then you have the kinetic energy, which is written this way. Okay, that's typically how such an Hamiltonian look like, and W, V will depend on which system you're considering. And then Newton's laws of motion, they are encoded in a certain dynamic on the system, and these are Hamiltonian dynamics, and they are written as follows. The positions, they evolve like this, and the momentum, or the momenta, they act like this. Okay. Of course, you assume that there is enough regularity on H and so on.
Sorry, the last line is not readable.
Oh, I'm sorry.
Could you start a new page,
okay.
please?
Okay, sure. Yeah, that's better. Thank you. Yeah, so these are the equations of motion when using the Hamiltonian formalism. Okay, and so and if you follow the motion, well, you have a flow, and so X, which is the state, belongs to some gamma, which here was really a RD times RD to the n. But it could be something more general. It could be a sub-manifold of this, and that will be the phase space. And the solving Hamilton's equations, well, it gives you a flow on gamma. So if you start somewhere, then at every time you're transported somewhere else, and that goes from gamma to gamma. Okay, and that's the evolution of the system for the classical mechanics. Okay, and here's one first important remark. It's more than a remark, actually. It's Liouville's theorem tells you that the volume in so the usual volume on gamma, the volume form, if you want, or the volume in RD times RD to the n, the Leblé measure, is invariant under the flow. So what that means is that if you think that this is your big phase space, and you start, if you look at some portion of phase space, A, and then you let everyone evolve, you will end up somewhere else. That's not a very realistic picture, because precisely what I want to say is that, or maybe it's going to be deformed, actually. Maybe it's not going to look at all this, but okay. You'll get phi T of A, and they have the same area. So the volume in phase space, which is sometimes called the phase extension. Honestly, I have rarely seen this, but okay, is a constant of motion. Okay, or it's a okay. So that's one thing that's good to keep in mind. And of course, here we have linear PDEs, right? And if H is smooth enough, it's fairly reasonable that we can have all the good results we want, existence, uniqueness of solutions. So in principle, we could do physics like that. Just write down all the equations, take the initial condition for all the particles, and then solve, and then you will know whatever happens at all times, okay? So there is an obvious, or maybe not so obvious, there's a problem, which is not a theoretical problem, it's a practical problem. The practical problem is that n is huge. Right? So let me remind you that Avogadro's number, which is if you want, it's the typical order of magnitude for molecules or atoms in say in the air of in the atmosphere of the room, it's 10 to the 23. Okay, so it would require first of all solving an enormous number of equations, plus knowing the initial condition exactly for all these particles, and one can expect that these equations have chaotic properties. So if you make a small mistake in the measurements, you will get enormous mistakes after a short time. So this is not tractable. Okay. And so on the other hand, so that was the microscopic description. You could hope to work only with this, but it turns out to be not super realistic. On the other hand, you have thermodynamics. In thermodynamics, the claim is the system can be represented, if you want, effectively by much fewer parameters or quantities. So in fact, what is important for us as human beings is not the position and the momentum of every particle in the atmosphere of the room, but these are quantities like the temperature, or which is the average kinetic energy, actually, or the volume of the gas, or the pressure, or things like that, or maybe the mean energy, things like that. So the claim is that we can actually work with much fewer parameters, quantities, and they have there are some relationships between these quantities, and you can do physics with those. There is one important part of thermodynamics. So in you have rules of thermodynamics. These are empirical rules. There is rule 1, which is the conservation of energy. Which really means that if you have some kind of isolated system, then the internal energy does not change. Okay, and then there is a rule 2, which is the second principle of thermodynamics, which states the existence of some function f, s, of a function s, called the entropy, that has some properties that I will not try to pretend that I understand completely, okay? That has certain properties, okay? But what's important is just, first of all, is to understand that the second principle claims the existence of a certain function that has certain properties. If you want to know more about this, in a mathematical perspective, there are two celebrated papers by Leblé and Ingvason. It's called the mathematical and physical, the mathematics and physics of second law of thermodynamics. And there's a shorter version of it, which is a guide to entropy, blah, blah, blah. And they describe this mysterious second principle of thermodynamics in mathematical terms, and they prove theorems about it. And so in thermodynamics, you work with quantities like T, V, P, mean energy is usually U, and you have this entropy S, and then you have relations like things like du equals TdS minus P dV, things like that. These are so the idea is that you make small variations within the space of parameters, but you have these thermodynamical parameters, and they come with relationships. So you have relationships, and then you have models like the ideal gas or the van der Waals gas. So the same way that you could write laws of physics for how the particles interact at the microscale, you can write models for how these quantities behave at the large scale. And so where does statistical mechanics come? Well, it comes in between, okay? In a sense, comes in between. And the key input, the key epistemological revolution is that in statistical mechanics, you replace the deterministic micro dynamical description that I mentioned by a probabilistic. It's still micro, but now it's static, nothing moves. Description. And this description is encoded in certain ensembles that I will mention in a minute. Okay, and so these ensembles are random objects. They are actually probability measures on the space, on the state space. And then you try to derive average quantities and their relationships. Okay, so if I can quote again one of these great books that I mentioned at the beginning, in Friedle and Velenik, you can read the first step in statistical mechanics is to abandon the idea of providing a complete deterministic description of the system and to search instead for a probability distribution over the set. So I'm just going to mention that. So we are looking at, or we're looking for a probability distribution on the set, of all microstates, which is something that I haven't mentioned that word, but a microstate will just be an element in phase space. in the big space gamma that I wrote at the beginning. So we're looking for a probability distribution on the set of all macrostates, which would yield predictions compatible with the observed macrostate. So macrostate is a bit harder to define. I will try to, because there are actually several definitions. But of course, the idea is that, okay, we're going to change the point of view. We're going to look at something that's a random object. Okay, but of course, we still want to save the phenomenons, right? We want to, whatever prediction we're making, it has to have some connection with what we actually see in real life. Okay. So we want to connect micro and macro in a satisfying way. Maybe just to be brief, there's one test of validity. I will just mention it briefly. Is to check something that's called orthodicity. And in one word, it means maybe do, not does. Do our ensembles allow us to define an entropy functional. An entropy that behaves like the one of thermodynamics, like the one of thermodynamics. So I should put that in between parentheses. In a sense, it's kind of the basic thing you want to do apparently as a physicist. I learned that in Galavotti actually, but I had never heard of it before. And I think in a sense, this has been done at the beginning, and then we've checked that the ensembles that we work with, they are orthotics. And then no one cares about it anymore. But I just wanted to mention, because I learned it while preparing this lecture, and I thought it was an interesting kind of fun fact. Of course, there's a sanity check at the beginning of the theory, and it turns out to be not a completely trivial sanity check. It's done in the book of Galavotti. Okay, but then once we've passed that check, we can forget about it. Okay, so what are these ensembles? So there are many ensembles that you can work with in statistical mechanics. There are three main ones, and among these three, there is one main one. Okay, so three main ensembles. You may have met them already. There's there's micro, canonical, and grand canonical. So what is the micro-canonical ensemble? It consists in the following. It's meant to describe an isolated system. If you have an isolated system, it means that the total energy of the system is invariant. So I can write like say U0. Okay, so in the dynamical description, the energy will not change, and here we want to do a probabilistic description that has to, satisfy that fact that the energy is constant. Okay, and what could be simpler than looking at the uniform measure on all on the it's called the energy shell. So it's the subset of phase space such that the energy is U0. Okay. Of course, there will be some mathematical problems of definition. Is that a well-defined submanifold? Is H smooth enough? Can I give a sense of the uniform measure on that? But let's assume it's some kind of a sphere, maybe within maybe it's a codimension 1 surface, something like that. So in a sense, P of X will be 1 over the volume of the energy shell, indicator of the energy shell. Okay, so it's a very simple measure to write down. If you can define it, it's simple to write down. Perhaps if you have more of a physical mind, maybe you will take a small shell. Perhaps should be replaced by something like instead of looking at exactly energy exactly U0, you could write something like that, plus epsilon and then epsilon small. Maybe that's more satisfying in a physical perspective because the energy will never be exactly U0. Okay, whatever. Actually, what mathematicians work with is this kind of measure. Okay, so that's the micro-canonical ensemble. So if you work in the micro-canonical ensemble, it means that you make the assumption that the energy is constant, and then you take all the configurations that have this energy with equal probability. And then there's the canonical ensemble, which is the central object, really, for us. And that is meant to describe a system that is in contact with a heat bath or a heat reservoir, which means two things. It means the energy is not constant because you can exchange energy with whatever bath you're next to, but the temperature is fixed by this guy. Okay, so you may have energy exchange, but the temperature is fixed. So let T denote the temperature, and then the framework of the canonical ensemble is written this way. So as I told you, working with an ensemble just means if I go back to the quote of Friedli and Velenik, it means you choose a probability distribution on the set of all microstates. So the microcanonical was one. Here's a new one, and in this new framework, the probability of a state X is proportional to this thing, which is called the Boltzmann's factor. Okay, and as you can see, it's the energy divided by the temperature, and then there's a minus sign here. Okay, so if you have high energy, it's unlikely that you will be observed. That's what it transcribes. Person here is a very important object in statistical physics. It has a name. It's called the partition function. And it's, in a sense, it is simply a constant that makes the total mass equals to 1. So it's simply this.
There's a question. Just a moment, please.
Hello. So
Just talk.
Okay, just talk. Okay. So how do I make sense of the left-hand side and this? So you write dpx by dx?
Yes. Okay. So maybe so dx here is Lebesgue on gamma. If I see gamma as being part of RD times RD to the n, then certainly it's not a problem, right? I write it as a density which is absolutely continuous with respect to the Lebesgue measure on this. It's a big space, but it's still a product of R many times, okay? What may happen, so otherwise, if you work with gamma, which is if you want a non-standard phase space, maybe gamma is just some space in which your statistical physics live, then it has to come with some reference measure. If you want, if it's an abstract phase space, it has to come with dV. It should come with a reference measure dV, and then you compute the density with respect to dV. Okay.
And so how do I know that the total integral is finite?
You don't know. That's you don't know. If it's not, then the system is not well defined. I will come to that. No, so of course it depends on what is H. Maybe H, and I will actually give examples, I guess, next time of situations where the integral might not converge, and it precisely means that your system is unstable, or that there's a problem with the formulation of your system. So of course, the simplest setting is that if your phase space is finite and you have the reference measure is a counting measure and H is bounded, then that works. I mean, H is bounded because the space is finite. Or if you work on RD times RD and H is bounded, then it works. It's continuous and bounded. And then there are some weirder situations. So maybe I can take 2 minutes to write down the third ensemble and then I stop. Is that okay?
Yes, please.
Okay, thank you. So we'll come back on the canonical ensemble because it's the central object. But I want to mention the third member of the family, which is the grand canonical ensemble. And in the grand canonical ensemble is a little weirder, to me at least, because it's meant to describe a system that can exchange energy, but also particles. So the energy is not fixed, and the total number of particles is not fixed either. So you need a little bit more setup to define it. You need to define for each little n, which is the possible number of particles, you need to have some kind of phase space gamma n, and then some kind of Hamiltonian energy Hn. Okay, you will still need a temperature T, and you will need another parameter which is called the fugacity, which is denoted by Z usually. And if you have all these things, you can write down the probability that of observing X. Well, it's given by exponential minus Hn of X divided by T. Okay, but it has a certain and then you have to divide by a big, so it's a grand canonical. So what that means, and Z grand canonical is the sum over n of Zn integral over gamma n. So I guess it's something like it's dx in gamma n. It's a little weird, right? Okay, maybe one way to think about it is that first you're sampling the number of particles according to some geometric distribution with parameter z. Okay, and once you fixed the number of particles, you're back to a canonical ensemble. Okay, so that's grand canonical, and in the grand canonical ensemble, the number of particles is not fixed. Just one remark for the sake of it. You see, I'm writing H over T. This is not homogeneous, right? An energy and a temperature is not okay. So it really should be H over KBT, where KB is a Boltzmann constant. But I will forget about all these physical constants. But okay, so there should be a KB everywhere. Okay, maybe I'll stop here. today, and then we can discuss later. Thank you for your attention.